What's up, y'all? And today I'm currently here in another video. We're gonna go through like equivalent neutral class. This particular topic is in inorganic chemistry, and so if you're currently taking inorganic chemistry, this video may be for you. So, equivalent neutral class. What do we think of equivalent neutral class? Well, in inorganic chemistry, we always use configurations to characterize our complex center, and there's a very common configuration that we use, an electronic configuration, MLXZ, and that determines how many X ligands you have, how many L ligands you have, and how many Z ligands you have. But sometimes this particular complex, a particular complex you're given in inorganic might have a charge, and so determining the configuration might be a little bit tedious. And so in this example, we can focus on one of the charge complexes here. This is a ruthenium 1 complex because it has a positive 1. So if you look closely, I labeled it as positive 1. I sure hope that it's clear that it's positive 1. And these are all ligands that are attached to the ruthenium. So this is a PPH2, 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 and then this is a PPH3. These are all ligands. So this specifically would be considered as a bidentate. It bites the metal twice. The same thing here. And then there's also an alkyl group attached as a ligand. This is X. And so let's start counting them up. So to form the MLXZ configuration for this molecule, it would be our L's, it's just one contributed by this ligand. This is a triphenylphosphine ligand, so keep that in mind. So it's just ML1, and there's 1, 2, 3, 4, 5 X's. So I'm gonna write that as MLX5. There is a positive 1 associated with the middle center, and so I'm gonna write that. And so normally these configurations are characterized without charges, but when you do get a charge, we can easily neutralize or clarify or remove the charge by using the equivalent neutral class. This is where the equivalent neutral class concept comes in handy. And so the equivalent neutral class informs us that when you have an X that is negatively charged, this is the same as an L. And when you have an L that is positively charged, this is the same as an X. I'm going to explain that. An X represents 1 electron. And this is a negative charge. A negative charge is also another electron. If you add these 2 electrons together, you get 2 electrons. And the L represents a lone pair. A lone pair constitutes 2 electrons. When you have a lone pair that is positively charged, so a lone pair is 2 electrons, but you have a positive particle, and so when you add them together, -2, the L's, since it's a lone pair and it's 2 electrons, we can represent that mathematically as -2. -2 plus 1 would give us -1 back. -1 represents 1 electron only, which is X. We represent X as an electron and a pair of electrons as a lone pair, which it would be 2 electrons. Hope that makes sense. So in this case, what can we do so that we can neutralize the charge in this configuration? Well, since we only have 1 L, and conventionally we know that L plus is X, why don't we just substitute that? So that means we're going to use the L, and then we end up with MXZ because L plus is equal to X, then that means we have to use up this L. So once we use it up, it becomes X because the L takes the charge of the plus. L plus is X. That's what happens here. So this is the new configuration. When we look at the case of this metal complex, what do we think? This is also positively charged, and it's connected by 3 L ligands. It's also connected by an X ligand. So let's write out the configuration. MLXZQ plus minus. It's usually plus minus Q. I should correct that. It's plus minus Q. So we have 3 L's and 1 X. And this is overall positively charged. And like I said before, when you have an L plus, according to the equivalent neutral class concept, this is equivalent to an X. And so when we apply this to the configuration, we end up with ML2 X2 because there's 3 L ligands, and one of the L ligands absorbed the charge to become L plus, and it formed X. And so that means you just increased your number of X and you decrease your number of L, because an L was used and to gain an X. So from L3 you drop down to L2, and because we formed an X, from X you now gain an extra X to form X2. Hope that was helpful. Okay, please like and subscribe. Comment in the comment section where you would want to see my explanation. Comment in the comment section also your favorite explanation in the video, and I'll see you on the other side. Thanks.